Assalamualaikum and hello, I'm Hanis Afifah and I'll be explaining part A question number 1. This is the table we refer to deduce the structure and the type of carbon. For hydrocarbon A, I deduced it as 2-methyl butene. This is because looking at the signals at 182 ppm and 180 ppm, both are C double bond C. The 132 ppm signal is a singlet, meaning it has no attached hydrogen. It is also more deshielded, so it appears further downfield. For the 180 ppm signal is a doublet, meaning it has one attached hydrogen. So it is slightly more shielded, which explains the lower shift. Next, we look at the signals at 26, 17, and 30 ppm, all appearing as quartets. This tells us that they are CH3 groups because each is split by the 3 attached hydrogens. 26 ppm is the CH3 next to the double bond, so it is more deshielded. The 17 ppm and 13 ppm signals come also attached on the C double bond C. They appear at different shift due to slight differences in their environment. For hydrocarbon B, I deduced it as 2-methyl-but-1-ene. This is because the signals at 147 ppm and 108 ppm are the two carbon double bond that attach to each other. 147 ppm has no hydrogen, so it is more deshielded, and 108 ppm has two attached hydrogen, making it the other end of the double bond carbon. Let's look at the other three signals. 31 ppm is the CH2 group that is directly connected to the double bond. It appears as a triplet because it is split by the two hydrogens on the neighboring CH3. 22 ppm is the methyl group attached to the double bond C. It is a quartet because of the three hydrogens splitting the attached carbon. Lastly, 13 ppm is the other methyl group on the branch further from the double bond, so it is more shielded and shows up further upfield.
Here we will now compare the mass spectra of 2-methyl-but-2-ene and also 2-methyl-but-1-ene. Both show a molecular ion at mass spectra ratio equal to 70, confirming that they have the same molecular formula. However, the base peak difference at hydrocarbon A has mass spectra ratio equal to 55 from a tertiary allylic cation, while hydrocarbon B shows mass spectra ratio equal to 56 from a less stable allylic carbocation. They are both share a common fragment at mass spectra ratio equal to 15, which is a methyl carbocation. This shows how the position of the double bond will influence the fragmentation. Now we are focusing on hydrocarbon A, which is 2-methyl-but-2-ene. The molecular ion appears at mass spectra ratio equal to 70 and the base peak at mass spectra ratio equal to 55 represent a C4H7 allylic carbocation formed after the loss of a methyl group. Other fragments included mass spectra ratio equal to 42 for C3H6 carbocation, mass spectra ratio equal to 27 for C2H3 carbocation, and mass spectra ratio equal to 15 for methyl carbocation. These are the classic products of allylic cleavage in branch alkenes. This spectrum will emphasize how 2-methyl-but-2-ene fragments, the double bond is at center, promoting the cleavage next to it. This will lead to a highly stable tertiary allylic cation enhanced by the resonance and also a hyperconjugation, giving the base peak at mass spectra ratio equal to 55. It will illustrate how the molecular branching favors certain fragment pathways. Hydrocarbon B also shows a molecular ions at mass spectra ratio equal to 70, but the base peak is mass spectra ratio equal to 56 from a C4H8 allylic cations. Other fragments include the mass spectra ratio equal to 41 from C3H5 carbocations, mass spectra ratio equal to 29 for C2H5, which is the ethyl carbocations, and again mass spectra ratio equal to 15 for methyl carbocations. This reflects a different fragmentation load due to the terminal double bonds. This spectrum confirms that 2-methyl-but-1-ene behave differently, while the molecular ion remain at mass spectra ratio equal to 70, the base peak at mass spectra ratio equal to 56 suggests a primary allylic carbocation, which is less stable compound compared to hydrocarbon A. The cleavage near the terminal double bond gives C3H5 carbocation at a mass spectra ratio equal to 41, and other fragmentation small ions like ethyl and methyl cations at mass spectra ratio equal to 29 and also mass spectra ratio equal to 15.
Hi and Assalamualaikum. My name is Maimuna with number matrix A202603. Today I will explain this particular combined instrumentation, which is Gcms, that stands for gas chromatography mass spectrometry, combination of Gc and Ms. It is a powerful analytical technique used to separate, identify and quantify compounds in complex mixtures. As for the concept, gas chromatography or GC is a technique that separates volatile components of a sample. The sample is vaporized and carried by an inert gas through a column coated with a stationary phase. Different compounds interact differently with this stationary phase, causing them to separate based on their retention times and resulting in chromatogram. GC is ideal for analyzing small molecules that can be vaporized without breaking down. Next, mass spectrometry or MS identify compounds by ionizing them and measuring their mass to charge ratios. This process produces a unique fragmentation pattern or mass spectrum, which acts like a molecular fingerprint that allows us to both identify and quantify compounds with high sensitivity and specificity. When combined, GC and MS offer a powerful advantage. GC first separates the mixture into individual components, and then MS identifies and quantifies each one. This dual confirmation by retention time and mass spectrum greatly help in qualitative and quantitative analysis, making GCMS highly reliable. This is the flow on how GCMS works. First, a syringe injects the volatile sample into the injector pot. An inert carrier gas like helium transports the sample through the column. Inside the column, compounds separate based on their interaction with the stationary phase and their boiling points. Separated compounds exit the GC column and move through a heated transfer line to prevent condensation, entering the mass spectrometer. In the MS, compounds are ionized in the ion source. The resulting ions are focused by lenses and separated in the mass analyzer based on their mass to charge ratios. The detector records these ions. The detector sends data to a computer system which produces a chromatogram and mass spectra for compound identification and quantification. Let's walk through the data analysis of GCMS and what information each tells us. The chromatogram is a plot showing detector response versus retention time. Each peak represents a different compound separated by the gas chromatograph. The detection time helps indicate which compound is present, as different substances travel through the column at different rates. The peak area or height is proportional to the concentration of the compound in the sample, making it useful for quantitative analysis. By examining the number, shape, and size of peaks, we can assess sample purity, complexity, and the relative amounts of each component. Next, the mass spectrum is a graph of ion abundance versus mass to charge ratio, MZ. Each compound produces a unique pattern of fragments which acts like a molecular fingerprint. The molecular ion peak, highest MZ, often indicates the molecular weight of the compound. The pattern of smaller fragment peaks provide structural information, helping deduce how the molecule breaks apart. By analyzing the spectrum, we can identify unknown compounds and confirm the identity of known ones. A reference library is a large database of known mass spectra for those of compounds. The library allows us to compare the sample's mass spectrum to source spectra for rapid identification. Matching the sample spectrum to a reference provides strong evidence for the compound's identity. Libraries also help flag unknowns when no close match is found, guiding further analysis. Using both retention time from the chromatogram and the spectral match from the library increases confidence in identification. Also, in GCMS analysis, 3D GCMS chromatogram can be produced, providing a richer and more detailed view of the sample. Retention time on the x-axis showing when each compound elutes from the gas chromatograph, ion intensity on the y-axis representing the abundance of detected ions at each time point, mass to charge ratio MZ on the z-axis indicating the mass of ion fragments detected by the mass spectrometer. This 3D plot allows us to visualize how the intensity of specific ion fragments changes over time, enabling simultaneous qualitative and quantitative analysis. Here are another example of 3D chromatogram. This is the GCMS instrument in the real life, which is GCMS QP2010 Plus. The basic components include sample injector, auto sampler, oven plus column, and mass analyzer plus detector. Finally, computer as the data analyzer. These are the detailed informations of the basic components of GCMS.
Hi and good day, my name is Wang Jingling, and I will now briefly present the applications of gas chromatography mass spectrometry GCMS. GCMS is a powerful analytical technique that combines the gas chromatography, which separates the volatile compounds, with mass spectrometry, which identifies and quantifies them based on their mass to charge ratio. This dual system produces both a chromatogram and a mass spectrum for precise qualitative and quantitative analysis. In environmental analysis, GCMS is widely used to detect the pollutants like volatile organic compounds (VOC), pesticides, and the dioxins in air, soil, and water. Environmental samples are isolated using the liquid-liquid or solid-liquid extraction, then separated by GC, and analytes are identified by their fragmentation patterns in MS. In forensic science, it serves two key roles. First, in drug and toxicology analysis, it detects the drugs and poisons such as morphine in blood or urine samples. Blood or urine is extracted, run through the GC for separation, and MS is to confirm the specific drugs or metabolites using the spectral libraries. Second, in fire debris analysis, it identifies the ignitable liquid residues like petrol or kerosene in fire debris. Volatile residues are recovered from the burned material, separated by GC and compared to the known accelerant spectra in MS. Its accuracy makes it admissible in court. In food safety analysis, Gcms detects the contaminants, illegal additives, and also profile the flavor compounds. It also used to identify the melamine contamination in milk, which caused a major food safety scandal. Food samples are isolated using the SPE, solid phase extraction, with GC separating the flavor or contaminant compounds and the MS confirming its identity. In pharmaceutical field, Gcms ensures the drug purity by detecting the residual solvents and impurities in the active pharmaceutical ingredients or APIs and the finished drug products. Drug products are isolated using the headspace sampling, and Gcms determines the residual solvent levels and impurities. It also supports the drug development and stability testing. One of the most fascinating uses of Gcms is in the space exploration. Gcms analyzing the chemical composition of planetary atmospheres, surfaces, and cometary material. For example, NASA's Curiosity rover uses a sample analysis at Mars SAM instrument composed of GC, MS, and a laser spectrometer to detect the organic molecules and analyze the Martian atmosphere. While GC has some limitations like only analyzing the volatile compounds and requiring complex preparation, recent advancements like 2D GC for the separation of more complex samples, high resolution of mass spectrometry, and portable instruments are expanding its capability. In conclusion, GCMS supports everything from the environmental to the planetary discovery. So that's all from our group. Thank you.